Are we okay with the voice? Okay, so directly we are going to start our class. Okay, so the last thing we have stopped at, the last thing that we have stopped at in um, classes before the test was the detailing. So today we are going to complete the detailing problem, or the detailing part of the problem. So now, if you remember, if we go to the question, you will see that the question is where we are having case number 4. Okay, where it's case number 4 for the bending moment diagram. Okay, which is 2 adjacent edges discontinuous, and we have said one short is going to be there and one long is going to be there. Okay, one long is discontinuous and one short is discontinuous. Okay, now if we take this particular drawing, okay, if we take this particular drawing, which is 4x, okay, okay. So if we take the drawing of bending moment for x, and we'll try to check the detailing according to whatever we have drawn for. Now you will see the bending moment diagram for x direction was of this shape, where we had x positive here and we had x negative here. Okay, so what does it mean? It means that I have the reinforcement of x. Okay, there will be a reinforcement of x in this direction, which is for the bottom. And we said for the bottom we are going to continue it from the beginning till the end, if you remember. And there is a negative bending moment, which is representing a top reinforcement. So there will be another reinforcement here for x. Okay, only for the position of the negative. After that, we are going to place our y. So these are going to be our y bar reinforcement according to whatever we have calculated in the AS provided. Okay, so that is going to be a section and this is going to be a plan. Anyhow, to make it a bit clearer, I'm just going to delete this one. We're going to see it step by step. So you can see this is going to be representing now once again according to the bending moment diagram. Okay, so we have x positive and we have x negative. Okay, so now the bottom reinforcement is representing x positive. Okay, this is what we can see in x direction section or longitudinal section, and this is what we can see in a plan. Okay, so this is how the plan is looking like. If you're seeing it from the top, one reinforcement, and then you will see the other reinforcement in white color. Okay, now after we finish the bottom reinforcement, we are going to go for the other side reinforcement, which is going to be your y positive. Okay, so this is going to be y positive. Now both of them are positive because they are acting on the bottom portion. Okay, they are acting on the bottom portion. So X positive and Y positive. Okay, so this is representing your bar, another one, and it goes on. Okay, so now we have what we have. We have the white, which is representing X positive, and then we have the black color, which is representing Y positive. After that, after we have finished the positive, now we come to the negative part. Now the negative part is only available at a certain location of the slab, which is available on the left side. So we are going to have some kind of reinforcement here, okay, which can be seen, okay. Which can be seen here in red color. This is representing now X negative according to whatever shape once again we have drawn. Okay. Now, of course, since there is X negative, slabs are two reinforcement, two sides reinforcement. So there should be a Y negative as well, even if it's minimal. So we have drawn the red color, which is representing now X negative. So this is X negative. And once again, we said this is going to be representing your X positive. This is your Y positive. And then we have the other bars of X negative in red color. After that, we have in gray or green here. This is representing your Y negative. Are we okay about the detailing? Are we fine about the detailing? The BVT is available in your Teams here. Okay. Are we okay? We have said from the beginning of the semester that the Teams, the PowerPoint is available in the Teams. Are we okay? Okay, we have finished from the detailing. Now I have already explained for you the concept of sunken slab. And there is another example in which I have told you I'm not going to solve, but I'm going to highlight the differences between the first example and the second example. If you see the main thing which is happening here, that we have two slabs. Okay, we have two slabs. This slab is having portions which are disconnected, and we have portions which are connected. Okay. So there is no case where you are having a portion of a slab to be disconnected and the other portion is connected. It's either fully connected or fully disconnected. Now we need to use our logic and our engineering judgment to solve this particular slab. So what we are going to do, we are going to cut it in the portion of difference between the disconnected and connected part. So now what we see, we'll take a line here, and then we'll take another line here. Now this is going to be taken in this portion. We are going to take it as discontinued, fully discontinued in terms of X. Okay. And the other side, we are going to take it discontinued from one part and then continued from the other part. Okay. Now this is in terms of X. In terms of Y, we are going to have one. Let's say that this is case number one, assuming that this is disconnected, this is disconnected, this is disconnected, and this is disconnected. So four elements are disconnected. So this is case number one. So this is going to be the bending moment for case number one. And then the other case, which is case number two, where we are assuming that this is disconnected, this is connected or continuous, this is disconnected, and this is disconnected, which is going to be case number two. Now here the bending moment between, for Y direction, the bending moment is the same, since this is disconnected and this is disconnected. But what happens? The values of case number one for Y, the values of case number one and case number two, values of case number one and case number two are not going to be the same. because we said the values of y are depending on the cases of x. Okay, so if you have your value of x is something, then it will give you a corresponding value of y. Okay, so the values of 1 and 2 for y direction are not the same. The shape of bending moment diagram is the same, but the values are not the same. Now for me, when I'm going to design which one to be chosen, now what I need to understand now in x, I have this shape and I have this shape. Now we have x positive and we have x positive. Among of this x positive and x positive, we are going to take the maximum of 2. Now if we have taken the maximum of 2, it's going to be safe in all along the slab. Okay, now when it comes to x negative, we have here x negative and here we have 0. Okay, so wherever there is a continuity, we are going to subtract of x. The other portion does not require x negative. Now on the side of y, we are going to have y1 and we are going to have y2. So which one we are going to take? Once again, we are going to take, both of them are positive, we are going to take the maximum of 2. Now if I design for the maximum, of course the minimum will be safe. Okay, once again for the negative, if you see the negative bending moment, in case number 1 for x, there is no negative bending moment, so I don't need to consider it. For the negative bending moment, in case number 2, there is a negative bending moment, so this negative bending moment will only be appearing wherever there is a continuity. The other side, there is no continuity, so for you there is no need to supply reinforcement. It is 0 only. Okay, now if you go and see the bending moment diagrams, you will understand further. Okay, I'll not go through the question. I'll explain something related to cover as well. But anyhow, so you can see that I have taken a section here and I have taken section here. Both sections are not the same. One of them is acting in x, acting to be discontinuous from both parts. Another one is discontinuous and then continuous on the other side. Okay, now if we go and take the first case, this is disconnected. So this is disconnected, this is disconnected, this is disconnected, and this is disconnected. Okay, so 4 sides are disconnected. Now case number 2 for the red color, this is disconnected from the beginning, this is disconnected, now this is connected, and this is disconnected. Okay, so if we go and see, this is a case where it's disconnected from all the sides. So I'm assuming this is the first case. The second case, I'm assuming that this is connected from one side. Okay, now whatever case, the real case of the slab is combining these two. It's combining that one side is continuous, another side is discontinuous. Now for me, I need to evaluate and analyze these two cases, and then I'll say which one to take or which bending moments to take. So what I'm going to do, you can see that the bending moment in both scenarios are different. Okay, now we have here, let's call this one to be x positive 1, and then we have x positive 2. Now since we have two values, I'll be taking the maximum of the 2. Now why I'm taking the maximum of the 2? If I'm taking the maximum of the 2, it will be safe for both scenarios. If I'm taking the lesser, it will be safe for one, it will be failing for the other one. Now this is in case of x positive. In case of x negative, we have only one value, so I don't need to compare it with something. I'll only take the x negative. Now for y, once again, there is a y here and there is a y there. Once again, y values are not going to be the same. Why? Because the case is different. Okay, so now we have y positive 1, and then we have y positive 2, and among these we are going to take the maximum as well. So if you go and see the values, So this is for case number 1. We have x positive and y positive. We have the coefficients. Everything has been shown. Okay, so we have the 0.103 and then we have 0.056. For the second case, once again, we are going to have their coefficients. So we have found the coefficients for the cases. Okay. Now for me, when I need to decide, you can see now we have beta x negative, we have beta x positive, we have beta y positive. Now if we go and see beta x positive here for this case is 0.069. For this case, it's 0.103. So this one should be taken as its highest value. Now for y positive, here it's 0.044. And then in the other case, it's going to be 0.056. So once again, this is going to be taken. Okay. So what I have done here, I have used my basic engineering to design this slab in which I took both cases, but I have ensured to use the most critical section, okay, in which we have evaluated the coefficients, and after that we have taken the maximum coefficient. Okay, now for the cover, now if you can see in this particular problem, we have it either continuous, either simple here. This is going to be for the calculation of cover and calculation of the ratio. If you remember, we have continuous and we have simple. Okay. So here we have it simple, and then here we have it continuous. Now, which one is going to be taken? You are going to be always taking the most critical situation, which is going to be simple. If you have two situations where simple and continuous, you're going to choose the simple. Now, if you go and see the values in terms of fire, we have simple and we have continuous. And always, if you can see, always you will see that the simple is going to be more critical. It's having more value than the continuous. 2020, 2020, 25, 20, 35, 25, 45, 35, 55, 45. So the most critical situation is going to be the simple. Okay. So if I use the simple, it will be safe for both continuous and simple. If I take the continuous case, it will be only safe for the continuous, and it will fail in the simple case. Okay. So now you should be having, or you should be okay with this particular solution. With this particular example, everything has been mentioned. I have only given you the hints on what is the difference between example number 1 and example number 2. Now, if you are able to solve example number 2 without issues, you should be able to design whatever rectangular two-way slab that you are facing. Okay. Now, after talking about the slabs, I have given you already one full problem, and then I have illustrated a different case. We have already explained shear, deflection, and everything. Things are going to be the same. The only thing, the cases, the values are going to change, the detailing as well. Now you can see here, we supplied only the top reinforcement. We have only supplied for the position where continuity is there. Now, if you remember, this is my slab. Now for my slab, this was disconnected, and there was a certain portion where it's connected. Okay. So now in this scenario, what you can see, I'll only supply the X negative reinforcement only where it's connected. Okay. So you can see that this portion was a portion where it's connected only. Okay. In the portions where there is no other slab, it does not need to be connected.
Sir?
Yes.
Sorry to interrupt you, but I have a question.
Yes.
For example 1, we find K, but the value of K that we find it from the rule is different than the value of K that we compare it with 0.156.
Which slide? Which K?
K value.
Yeah, which K? There are 4 Ks. Which K?
Yeah, this K that we find it from the rule M by this value is different than the K that we compare it with 0.156.
Which one? 0.025? Which
Yeah,
value? 4 values are there. Anyhow, if there is any problem with the values here, you can modify it yourself. This is a simple calculator thing. Whether it's 0, if it's 0.025 here, and then it's showing you, for example, here 0.029, you can modify and choose the correct answer. It's a calculator thing. Any other thing?
yes, sir. It's
Yeah.
0.09 and then we
0.
substitute.
You mean here it's showing 0.025 and there it's
Yes,
0.029? Yeah, this is
yes.
what I said for you. When you calculate, use the correct value.
Okay.
Okay. Any other question? Yes, if it's not rectangle, then you need to use your engineering judgments. Okay. So if the slab was continuous in one direction, so we would see the continuous lower column. I didn't understand whatever you have said. Can you clarify it, please?
Sir, I meant if the slab was continuous in one side, so we will not consider it as a simple, right? For example, if 1 hour resistance was given, so we look to the continuous row, right? This is
Yeah.
my question.
No, if it's continuous from which side, short or long?
Long.
No, if it's long, it does not matter because you are designing for the short always.
So if it was short.
No, if it was short and one side was continuous, then you should take the continuous.
Okay. And if it was in long direction, no matter, we can use the continuous and as it is simply.
The basic fundamentals is every judgment is going to be based on the short direction. So whatever happens in the long direction does not matter for you. Okay. Okay. Now going for the other part where we are going to talk about the transfer of loads. Okay. So now if you can see here, we are going to talk parallel to 3 or 4 slabs. Yeah, you need to know the case, which case is it, and then accordingly you can solve it, whether it's one side, 2 sides, 3 sides, 4 sides. Everything is going to be different in terms of the coefficient. Now when we see the transferring of loads to the beams, now of course the load of the slab will go and transfer to the beams. Okay, now to understand this particular thing, if you remember, you have studied this one already in design of structures 1, and you have studied it in theory of structures 2 in the yield lines. I don't want to spend a lot of time over there. Now if you can see here, this is my slab. Let's say that this is going to be my slab. Can you turn off your mic, please? Okay. So now what we can see, we have a slab. This slab is having Ly. This is my direction of, let's say, this is L1, the longer direction. And this is my shorter direction, that's Lx. Okay. Now we have one support here. This is my first support 1, and this is support 2. And if you remember, I have given you the idea of 2 people pulling the paper, if you remember. I don't know whether you remember or not, but anyhow. So 2 people pulling the paper. The paper will be cut in half because we have 2 people pulling only. Now, if 2 are pulling, okay, then half of the paper will go here for this side, and the other half is going to go to the other side. Now, if we try to analyze the beam in this scenario, if we try to analyze the beam, now I'm taking, for example, this beam. Okay, I'm taking this beam and calling it to be beam 1. Now, beam 1, okay, beam 1. Now, beam 1 is having a length of what exactly? What is the length of B1? You will see that the length of B1 is going to be Ly. Okay, the length of B1 is going to be Ly. Whatever length here is going to be the same as here. Okay, Ly. Now, what's the intensity of the load? The intensity of the load is going to be this portion. How much is the load? Okay, so the intensity of load is going to be, what is this distance? Now, this distance, the whole distance from here to here, we have already illustrated it as Lx. So half of it from here to here is going to be Lx over 2. So this intensity of the load is going to be Lx over 2. Okay, and this is what is shown here, Ls, which is short, or Lx. That depends on your letters. So Ls is referring to short, or Lx is referring to short. Both of them are fine. Okay, so this is how the loading is going to come to the UD, to the beam. Okay, this is how the loading is going to come to the beam in case of a one-way slab with 2 beams only. Now, going for showing you how the behavior is going to happen. The behavior is going to happen in this way. So half of the slab will be taken by the first support, and the other half is going to go for the second support. Okay, this is the example of the paper that I have given you. If you remember pulling it from both sides, you are going to get half here and half. Now, in case of a two-way, whether it's a one-way slab or a two-way slab supported by 4 beams, now if it's supported by 4 beams, now once again what we are going to have, this portion from here to here acting to be our Ly, and this portion from here to here is acting to be your Lx. Now, since there are 4 beams, it means that there are 4 regions. You can see that this is region number 1, region number 2, region number 3, and then region number 4. Okay, this is what you can see before going. This is what you can see here when we are pulling. 4 people are pulling, whether it's a square or whether it's a rectangle. The same concept is going. Now, for us, we need to understand. Now there are 4 beams. There is one short, so let us call this one to be short. This is another short beam. This is a long beam. This is a long beam. So we have 2 long and 2 short beams. Okay. Now, if we try to analyze the long beam, okay, if we try to take the long beam, so this is my long beam. Now, the long beam is supported by a column here, another column here. So I can draw that there is a support here. There is another support here. Okay. Now, after we finish putting the supports, I need to know the loading. Or we can say that the length of this is going to be our Ly. The length of the longer beam is going to be Ly. Now, while for the other scenario where we are going to have it for the short, the length of short beam is going to be Lx. And once again, there is a column here, there is a column. Now, after we check the behavior, we said that there will be trapezoidal and triangles. Now you can see the big one, the big beam, is taking the trapezoidal. So we have trapezoidal here. And then the short beam is taking a triangle. Okay. If you remember, when we have taken the yield lines, you will see that the long one is going to take a trapezoidal, the short one is going to take a triangle. This is what you have studied for a long time already. Now, for us, what I need to know how much is the intensity here. What are these intensities? Now, for me to understand the intensities, I need to go and understand once again. So here we have, this is my slab. where this is my Lx and this is going to be represented my Ly. Now the first thing that I need to do, let us try to draw these particular lines. So I have drawn the trapezoidals. Now the first thing, no, of course it's not load divided by area. Okay, load divided by area is a wrong concept. Okay, now if you can see here, we have Lx and we have Ly. Now the first thing, I need to get this particular dimension, and we said this particular dimension is the one acting here. Okay, now can we know what is this particular portion? Is it possible for us to know how much is this? Can we know how much is this dimension? Now if you can see, this dimension is half of x, half of Lx, right? In real structures, you cannot say they are fixed or they are hinged. They are semi-rigid normally. Okay, so we have here, okay, we have here this height as Lx over 2. So I can say now this height is Lx over 2. So if this is my Lx over 2, then of course this is going to be my Lx over 2. Okay, so we have Lx over 2. Okay, now if we come to this particular, length, can you tell me what is the length here? What is the angle here? What is the angle produced? Okay. Okay, the angle, this angle, the small angle. Okay, the angle produced is 45. Okay, so tan of 45 is going to give you 1. Okay, tan of 45 is going to give you 1. So if this is Lx over 2, then this is going to give you Lx over 2 as well. Right? Okay, so this is going to give you Lx over 2. So now we have the height of the triangle. We have the height of the trapezoidal. We know that this portion from here to here is Lx over 2. So this is going to be as well Lx over 2. Okay, Lx over 2. So if this is my Lx over 2 and this is my Lx over 2, then how much is this particular portion? How much is this particular portion? Now you can see that that particular portion is Ly minus Lx over 2 minus Lx over 2, which is going to give you Ly minus Lx. Okay, there's no Lx over 8. We don't have Lx over 8. Okay, so whatever is the scenario, whatever are the values that you are having, whatever your values that you are having, it's always going to be the intensity of the triangle, the intensity of the trapezoidal is going to be always Lx over 2. Okay, now if we go and see, you will see that this is going to be Lx over 2 and this is going to be Lx over 2. Okay, now the most important thing why we are studying this one is to understand how to transfer the loads from the slabs to the beams. Okay? From the slabs to the beams. Now there is another case where it's a cantilever. Now you can see this is the slab. Now this slab is not having any beam here. There is no beam here. There is no beam here. There is only one beam which is here. So of course all the load of the beam or all the load of the slab will be taken by the beam. Okay. Now if I try to draw the beam, this is my beam. Okay, this is my beam. The beam is supported by a column here, so I have drawn the column. Another column, so I have drawn here. Okay. And then now what's the intensity of the load? The intensity of the load is going to be the total length of the slab. Okay, which is going to be now in this scenario Lx or L effective. Okay. Are we clear? Are we fine? These are basic things that you should have already studied. Okay. Okay. Now this is how the negative reinforcement look like. Now a lot of people are asking how the negative reinforcement will be coming up and how the positive reinforcement is going to go down. Now the negative reinforcement will be coming at the top of the beam. Okay, there will be a beam at the top of the beam. There will be a negative reinforcement as you are seeing right now. Okay, so whatever has been illustrated here, you can see it's available above the beam, and this is how it looks like. Okay. Hopefully if things are okay, we'll try to arrange for you. Hopefully, if the situation is better, we'll be arranging for you a site visit where you can see all of these things. Okay. Now we studied the concept. We have studied the basics over there. We need to act as a support for what? For the slab? Yes, of course. Slab is supported by beam is supported by a column is supported by a foundation, and it goes on. This is a very basic thing. Anyhow, let us see how we are going to use whatever engineering or whatever fundamentals that we have studied right now. So it says for you, a problem says for you that a composite floor consisting of a 150 mm thick reinforced concrete slab supported on steel beams spanning 7 meters and spaced at 3 meter centers is to be designed to carry an imposed load of 3.5 kilonewton per meter square. If the unit mass of the steel beams is 50 kilogram per meter run, calculate the design loads on a typical internal beam. And then they have showed for us that there is there is this particular figure, and they have told us, okay, they told us that the beams are spanning 7 meters. So each beam we have, this is acting as beam 1, beam 2, beam 3, and then this is going to be beam number 4. Okay. Now the span of each beam has been given by the problem to be 7 meters. It says spanning 7 meters. And then each and every beam are spanned 3 meters away. So the distance between one span to another span, or one beam to another beam, is 3 meters. Now what we need to understand, the question is asking us to calculate for an internal beam. So internal beams are beams which are inside. So they have illustrated in the problem, they have illustrated for you that this is an internal beam. Okay, this is an internal beam. So the internal beam now is between two slabs. So this is slab number 1 and this is slab number 2. Okay, so this is S1 and this is S2. Okay, now what we need to see, we need to know that here we have beam number 4 This is beam number 3, and this is beam number 2. We don't have beams here. There are no beams. Okay, it's a one-way slab. We don't have beams on the other sides. So now if I take slab number 2 separately, and there is beam number 4 here, and there is beam number 3 here, I'll understand that half of the slab will go for 3 and the other half is going to go to 4. The same scenario for slab number 1. So slab number 1, S1 and S2 are only numbers, only numbers to make it clear for you. So S1, here we have B3 and here we have B2. Now once again, half of the slab 1 will go to beam 3 and the other half is going to go to beam 2. Okay, now what I can see that beam number 3 actually is taking 2 areas. It's taking half of S1 and it's taking half of S2. And this is what has been illustrated here. Okay, so now for me, okay, now after I have understood the what you call the areas and how many areas this particular beam is taking, I need to go and calculate the loading common on the beam. So for me, load on beam actually will be consisting of 2 things. One is the self weight of the beam, or let us say 3 things: self weight of the beam, wall, if there is any wall on the beam, and then we have load from the slab. Okay, so we'll try to draw the cases. Now, is there any self weight of the beam? Is there any self weight of the beam given? Is there any self weight of the beam given? Can we have a beam without self weight? Can we have a beam without self weight? Is it possible to delete the self weight of the beam? No, it's not possible. So it should be there. Okay, it should be there. Okay, it should be there. Now, what about the wall load? Did they specify for you anything related to wall now? Did they specify anything related to wall? No. So in this problem, no walls have been mentioned, so it's going to be no. What about loads from slabs? Do we have slabs? Do we have slabs? Okay, we have slabs. So two things we need to calculate here. The third one is not given, so it will not be calculated. So we need to calculate the self. Let us first calculate the let us have scenario number 1. So in scenario number 1, we are having self weight. So the self weight will be a UDL, right? The self weight will look like a UDL, right? Do you agree that the self weight is going to be all over the beam from the beginning till the end? Do you agree with this thing? Or it's only available in certain location? It's available all over, right? It's available all over. Now you can see here, it says for you the unit mass of the steel beam. So we have steel beams, and the unit mass of the steel beam is 50 kilogram per meter. Okay, so we have the load of the beam. So self weight of the beam is going to be 50 kilogram per meter, which will be equal to 0.5 kilonewton per meter. If you remember, we said to convert from kilogram to kilonewton, we need to divide by 100, if you remember. Okay, so 50 kilogram per meter is equal to 0.5 kilonewton per meter. Okay, are we fine? Are we fine till now? Okay, now just create another new slide so we can write on it directly. Okay, now going here. Now the other load, which is loads from slabs. Okay, loads from slabs. Now the first thing I need to understand the shape. Was it a UDL or is it a triangle and trapezoidal? So this is my beam. It's having 7 meter length. Now in our problem, was it a UDL or is it a triangle and trapezoidal? In this scenario, do we have the shape of the loading to be UDL or we have it as triangle and trapezoidal? It's a UDL only. Okay, it's a UDL only. So now we know. Okay, we know that the intensity of the loading is Lx over 2. We just took it. That the intensity of the loading is, or the height of the intensity is Lx over 2. Now Lx over 2, now if you go and see your slabs, we have the slab now is 7 to 3. Okay, if we see our problem, the slabs are actually 7 meter into 3 meter. Okay, 7 meter into 3 meter. So what is my short? What is my short? My short is 3 meter. So this is going to be 3 divided by 2. That's going to be 1.5 meter. Are we okay? Are we fine? Okay, very good. Now the loading is having a unit of meter. Do we have the loading to be in unit of meter? Is there any loading of a unit of meter? Once again, do we have any loading having a unit of meter? No, we don't have any loading with a unit of meter. Meter is a unit of length only. Okay, so what we need to do, this particular length, we need to understand it. We need to multiply it by something to get the value. Now, if you remember, in your slabs, you calculated the value of W, and this W was kilonewton per meter square. Okay. Now, if you can see what does this mean? What does this mean? You can see that this means over a length of 1 meter and a height of 1 meter, there will be a value of W. Okay. For a length of 1 meter and a height of 1 meter, there will be a value equal to W. Are we okay? So my W has been divided into 1 meter square. Okay. Now we need to calculate our W. We need to calculate our W. Going for W. Now if you see W is actually equal to 1.4 into dead load plus 1.6 into live load. Now going for the problem. Okay, going for the problem. Now the live load has been given in the problem. The live load has been given in the problem that it's equal to 3.5 kilonewton per meter square. Okay, so we are going to have 1.4. We need to check what's your dead load plus 1.6 multiplied by 3.5. Now, did they mention any dead load in the problem? Did they mention any dead load in the problem? Did they mention any dead load in the problem on the slab? Okay. The only dead load which is available, is the self weight of the slab itself. Okay. The only load or the only dead load available, on the slab is the self weight of the slab itself. Are we clear? The only dead load available on the slab is the self weight of the slab itself. Okay. Now I have already taught you how to calculate the self weight of the slab. So we have 24 multiplied by the thickness. The thickness has been given as 150. So we need to divide it by 1000. So it's going to be 24 into 0.15. Okay. Now can you give me this value? Can you give me this value? Can you give me this value? Total value, the total value. So the total value, according to you, is 10.64 kilonewton per meter square. Because you don't know how much is the steel. How much is the steel inside the concrete, Suleiman? And the second thing, the unit weight, which is 24, that is for reinforced concrete. So there is already an assumption of steel available. Are we clear, Suleiman? Is it clear? So if you go and see in the BS codes, if you refer back to BS 648, you will see that concrete unit weight is somehow different. Reinforced concrete is somehow different. Okay, so now this is 10.64. Now 10.64 is for how many meter height? 20. I mean, the 10.64 is for how much meter height, or how many meters of height? Who said? Once again, 10.64 is the loading for what area? It is for an area of 1 meter into 1 meter. Okay, it's an area for 1 meter into 1 meter. Okay, that's why we say kilonewton per meter square. Okay, so it's meter into meter. Now, what is the intensity of our height? What is the intensity of our height? There is no slab made of steel, Amira. That's the first thing. Second thing, it has been said for you that it is 150 mm thick reinforced concrete slab. Okay, so once again, 10.64 is for 1 meter height. If we want to calculate for a height of 1.5 meter, then this should be multiplied by 1.5 meter. Now, can you give me the total value here? Once again, whatever I'm saying for you, for 1 meter height, it's 10.64. For 1.5 meter height, how much is it? It is going to be more than 10.64, of course. Are we clear? Is it clear, or do I need to explain it further? Once again, for 1 meter into 1 meter, it's 10.64. Now our intensity No, you need to multiply by only 1.5. We are taking only one slab now, because the other half is going to go to the other slab, Suleiman. The other 1.5 is going to go to the other beam, not the other slab. Okay. Now we have got it to be 15.96. Now this is for how many slabs? We have done now the analysis for how many slabs. Let's say that this is slab number 2. This is whatever we have done right now is for how many slabs? Whatever calculation we have done now for how many slabs? We have taken, if you concentrated, we have only taken one slab. Now the beam that we are talking about is affected by how many slabs? The beam that we are taking into consideration is affected by how many slabs? By 2 slabs. So the loading of this is a beam number 3. You can see it's affected by this slab and it's affected by the other slab. Okay, it's affected by 2 slabs, right? We have calculated the loading for one slab. Now both slab number 1 and slab number 2, both slab number 1 and slab number 2 are exactly the same. Okay, are exactly the same, right? So once again, what we have done, we have only calculated this portion. Now the beam, which is beam number 3, needs to take both of them. So what we need to do, we need to go and now multiply loads from slabs. We need to multiply it by the number of slabs. So there are 2 slabs. So this is going to give you how much? So 31.92 kilonewton per meter. Is it clear? Are we okay? Okay. Now returning back here. So we have final, let's say, so the final load on beam is going to be 31.92 plus 0.5 multiplied by 1.4. 31.92 is the load coming from the slab. 0.5 is the self weight. 1.4 is the factor of safety for the self weight. Self weight is a dead load, right? Self weight, is it a dead load or a live load? We said, if you remember, 0.5 kilonewton per meter is the self weight of the beam. We didn't multiply it by any factor of safety. So now we multiplied it by a factor of safety. That's going to be 1.4. So what's your final value? I think it's going to be 32.62. And this is the final answer of the question. Are we clear? Are we clear? If we have a wall, then you need to calculate for the wall. Okay. Second question, question number 2. So it says for you a composite floor consisting of 150 mm thick reinforced concrete slab. No, we don't need, because it's a UDL. Suleiman, it's a UDL. It should be along the length only. If you are multiplying it, then it will turn to be a point. Once again, the loading was in kilonewton per meter square. That's how the loading in a slab. Now that loading should be shifted to a UDL. That's why we only multiply it by one dimension. If you multiply it by 2 dimensions, then it's going to turn up to be a point load rather than a UDL. Okay, so same question. The only thing that now it's going to be 6 meter and 3 meters, so it's going to be two-way slab. So that's why we are having 4 beams. I mean, all the sides we are having beams. And then they said for you, calculate the design loads on a typical internal beam. Okay. So we're going to solve it once again together. Once again, we are going to solve it together. So we have already got our value of loads from the slabs. Okay, we have got it to be 10.64. Okay, we have got it to be 10.64 multiplied, or let us say W, the value of W. How much? 64. Okay, so 10.64. Now they are the same because the life load here we have a 3.5. In the previous problem we have a 3.5. The thickness of the slab is 150. In the other problem it's 150 as well. So W is going to be the same. Are we clear? Are we fine? So now we want to calculate for 2 beams actually. We want to calculate, let us say, for this beam. Let us say I want to calculate now for this beam. Beam 1, beam 2, and then I want to calculate for beam 3. 3 beams. Okay, I want to calculate for 3 beams. Now, beam number 1, you can see if we try to draw the yield line. Okay, beam number 1 is going to take a trapezoidal. Beam number 2 is going to take a triangle. Beam number 3 is going to take 2 trapezoidals actually. Okay, so if we go and see beam number 1, for beam number 1 case, this is my 6 meter. Okay, this is my 6 meter. This 6 meter is going to take a trapezoidal. What is the intensity of the trapezoidal? Once again, the intensity is Lx over 2, if you remember. So that's going to give you once again 1.5. So W, okay, W final, let's say, is going to equal to 10.64 multiplied by 1.5 once again. Okay, 1.5 once again. That is going to give you how much? How much we are going to have now? 15.96 once again, kilonewton per meter. So what is the loading here? What is the value of loading here? What is the value of loading on this point? On this point it's 0. Here it's 15.96. Okay. Now if we want to get load on beam 1, okay, the load on beam 1 is going to be 15.96 plus 1.4 multiplied by 0.5 once again. So how much is that going to be? You should be getting it exactly as the same problem. You are going to get it as, how much you said? 16.66 kilonewton per meter. Okay, 16.66 kilonewton per meter. Are we clear? Is it clear? Okay. Now going for another one. Now in case of the triangle, so the triangle is going to be 3 meters. And once again, we have said it's going to be Lx over 2, that is 3 over 2, so it's 1.5 meter. My W, we have got it previously as, how much? YT beams, Suleiman. Okay, we have got it how much? 10.64 kilonewton per meter square multiplied by 1.5. Okay. So that's going to give you 15.96 kilonewton per meter. And once again, the final total loading on beam 2, we are going to have 15.96 plus 0.5 to 1.4, and this is going to give you once again 16.66 kilonewton per meter. Okay. Suleiman, it's not necessary. Normally, in most of the design, in most of the software, we only use rectangular section for the design, unless you want the T section or the flange section to take certain part of the bending from the slab. Okay. Now that can be inputted in the software, but normally we design the sections to be rectangular, although for certain sections T is going to be more economical. Okay. Are we clear about the triangle? Are we clear about beam number 2 on the triangle? Yes, same value. Okay. Same value, but of course the bending moment is not going to be the same, because the bending moment is depending on the span. One is having a span of 3 meters, another one is having a span of 6 meters. Okay. Are we fine? It depends on the problem and the height. It depends on Lx, but normally, yes, for a rectangle and trapezoidal, you will be getting the same. Or the same problem, but not all of the problems you will get 16.66. Okay, remaining is beam number 3, and I don't think that there is a huge issue on beam number 3, where the only thing that you need to multiply 2 times of W, so 15.96 multiplied by 2, and then add it with 1.4 and 2.5. You will get the final answer. Are we clear? Once again, a trapezoidal plus another trapezoidal are equal to one trapezoidal. one big trapezoid. Now if this one is 15.96 and this is 15.96, so this is going to be 15.96 multiplied by 2 plus we need to add 1.4 into 0.5. You shouldn't multiply the 1.4 into 0.5 two times because it's one beam only. You need to calculate it. So 15.96 for the first one, 15.96 for the second one, plus the self weight because we have only one beam. That's why we don't multiply this value by 2. Because if you multiply this value by 2, it means that you have multiplied 2 self weights and it's only one beam. So you shouldn't do that. So 15.96 multiplied by 2, since there are 2 trapezoidals, plus the self weight of one beam. Are we okay?
Mister?
Yes.
Can you please say it again? Why the last one did you multiply it by 2?
Because there are 2 trapezoidals. If you go and see this beam number 3, it's taking 2 trapezoidals. This is number 1 and this is number 2. Whatever is the value, values does not matter a lot for me, or do not matter a lot for me. As long as you understood, you can get the values. Are we clear? Okay. Shall we go to the other problem? Shall we go to the other problem? Okay. Now this is a good problem with.
Mister,
Yes.
We multiplied 1.4 into 0.5, again 1.4 into self weight. We do it
Where?
twice because it's two-way.
Where?
In the question.
Why would you multiply by 2 if there is only one beam? The
Okay,
self
okay.
weight will be once only. It's only one beam.
I know it's 1, but why we multiplied 1.4 into 0.5?
Because 0.5 is a weight given. That's 50. 1.4 because it's a dead loop.
Okay, now clear. Thank you.
Any other questions? Okay. Okay, let's go for this question. Now it says for you the floor shown below with an overall depth of 225 is to be designed to carry an imposed load of 3 kilonewton per meter square plus floor finishes and ceiling load of 1 kilonewton per meter square. Calculate the loading or design loads acting on beams B1, C1. So we are referring to B1 to C1. Okay, so B1 to C1, right? B1 to C1. So we want to calculate this one first, beam number 1. And then we have B2, C2. So we have B2. So B2 and then C2 once again. Okay, so this is beam number 2. Okay. And then we have B1 to B3. So we have B1 to B3. So this is going to be beam number 3 now. And then we have columns B1 and C1. Okay, so you are requested to calculate as well B1. So this column, so this is C1, column number 1. Okay, and then we have C1. So this is going to be your column number 2. So you are requested, okay, you are requested to calculate for 3 beams and 2 columns. Okay, the self weights of the beams and the columns have been given already to you. They have said as well that you need, or they have given you already, the columns are 3.5 meter in height, beams are 300 millimeter in depth, and let us say consider appropriate full load. Okay, now how would you calculate the wall load? How would you calculate the wall load? Most of you have already finished your project. You should know how to calculate your self wall, the weight of the wall. Similar to beam load. Okay, so how? From where you will get the wall load? Any idea? How much is the wall load? I'm asking the same thing. Everyone is telling me that height of the wall multiplied by the weight or by the load. How much is the load? That is the question. Okay. Density into B into D. So what's the density? 24 into depth of wall. You cannot use 24, Suleiman. You cannot use 24, Zahra. Your wall is a concrete block. It's not a reinforced concrete. What is the density of the block? $20. Okay, so 20. Can you calculate for me the weight for 1 meter? Can you calculate for me the loading for 1 meter height? $20, $24. Okay, I'm just trying to help you because this question is going to be the second question for extra marks. So I'll not solve it for you. Okay, so I'll give you a hint. Okay? I'll give you a hint. Okay, so I'll give you a hint, but you need to give me something back as well. Okay, so now you can see here from this table, it has been mentioned that if you are having a whole block work partition, it's going to be 315. So 315 kilogram per meter square. It means 3.15 kilonewton per meter square. Okay, so that's the load of the wall according to the table given. Now, since I have given you already a hint, okay, since I have given you already a hint, the thing that you need to do to get the extra marks for your test one are two things. Okay, are two things. Number one, you need to tell me how this 3.15 came up. Okay, how did we calculate this 3.15 based on what exactly? Okay, so use your density, whatever, 24, height. Already they have given you that the thickness is 200. Here in Oman, we are using 200 into 400 into 200. Right? In Oman, we are using blocks of 400 into 200 into 200, or 390 into 190 into 190. Okay, once again, two things that you need to do to get the extra mark for your test number one, or you don't want extra marks. Okay, we want. Okay. So two things. I have already told you that you need to go and solve that question for me. Okay. So the deadline, once again, the deadline for everyone, it's today, 11:59 p.m. There will not be any extension anymore. I'll not extend for any person. It's 11:59 today. Okay. So what I want from you, I told you that you need to go and solve a problem, which I have already explained most of the things inside. Okay. Okay. So this problem, I have told you, you need to solve this problem fully, whether it's beam or column. I didn't teach you the column, but you can use your logic to do for the column. Okay, so beams are there, 3 beams are there, and 2 columns. The only big issue that will face you is to consider the appropriate wall load. So I have given you the hint how to use wall load from this particular slide. Okay, now I have told you we can use 3.15 kilonewton per meter square for your hollow block. Now, since I have given you a hint, you need to repay it for me by answering me once again how this 3.15 was calculated. Okay, so you have from 3:30 to 11:59 to answer that question and to tell me how come this 3:15 came up. If you answered correctly these two, you will get extra 2 marks in your test number 1. Okay, so it's a challenge for you to do the beams, the columns, whatever 3 beams are there, 2 columns over there, and to tell me how come this 3:15 came up. You can use whatever thing you want, whether it's 20, 24, mortar, with mortar, without, combined with mortar. It's up to you. You have 6 hours of, more than 6 hours of searching, and you can search for an answer. Are we okay? And this is optional for those who want. It's up to you. For those who does not, it's up to you as well. Yes, Bushra, tell me. Okay. Now, for your attendance, just 1 second. For your attendance, can everyone write 3:30 p.m.? If the time came before 3:30 and you didn't write, you will not be considered as attended. Okay? So if 3:30 came in the timer in front of me, your attendance will not be taken into account. Yeah, this is what I said, 11:59. And it's a problem that most of the things have been already illustrated for you. 3:30 in Oman, Suleiman. So 11:59 Oman's time. Okay. Okay, good. Any questions that you have before? Any questions that you have before ending up this class? Bushra, waiting for your no. No is related to what exactly?